talking about factoring polynomials and how it relates to their roots and zeros, still on the parabola, so on quadratic equations. But for the bell work, it says the surface area of the cube is 6 times the quantity of a divided by 4 squared, where a is a positive constant. Which of the following gives the perimeter of one face of the cube? So a cube is kind of like a dice, right? It has 6 sides. They're all equal sided. To find the surface area of that, what you would do is you would find one area or the area of one side and then multiply it by 6. So from this surface area equation, it's 6 times a divided by 4 squared. Okay, to get from this to just one side of the cube, we would divide by 6. So those two 6s would cancel out and we would be left with a over 4 squared. Okay, if you remember anything about from geometry talking about area of a quadrilateral, it'll say that you take length times width or height times width, length, however you want to look at it. But you can see that this is squared. So what this means is that one side of our cube, we're to find the area here, the distance or the side length is a divided by 4. The perimeter is taking these side lengths and then multiplying 1 by 4, adding them all up. This side plus this side plus this side plus this side. Or you could just multiply one side length by 4. So 4 times one of our side lengths. Those two would cross out, and we're going to be just left with A as the perimeter of our cube. So once again, the surface area, it's the area of one side multiplied by 6. So you divide it by 6 to get back to the area of just one side. And then the area of one side is the square of a divided by 4, because that's our length and width since we're dealing in a square. So if we multiply 4 times a divided by 4, we are left with a, which would give you the perimeter of the cube, of one face of the cube. All right, off to lecture. Close that window because I won't need that. First, only 17 kids. That's perfect. But, yeah. Not a factor. Okay, so 5-minute check. We are to simplify the square root of a negative 125. So remember, when you're dealing with these types of problems, we want to find the perfect square that goes into them. And in all reality, we're going to blow it all apart and then simplify it using the square roots. Remember, the product rule of radicals states that we can divide this into the square root of negative 1, the square root of 25 times the square root of 5. Okay, 5 times 25 gives you 125 times the negative 1 gives you negative 1, or negative 125. So at this point, we have two perfect squares that we can solve. Square root of negative 1, which is I. Square root of 25, which is 5. And the square root of 5, we can't do anything with. So if we push all of these back together, because they're going to be multiplied, we would get 5i times the square root of 5. Okay, whenever you're simplifying, we blow it apart. We simplify the squares that we can. And then we have our simplified exact answer. This one, once again, a negative 128, the square root of a negative 128 with x to the 4th power. So to simplify this, once again, we want to think which square can possibly go into it. So the square root of negative 128, x to the 4th, that can be broken down into the square root of negative 1 times the square root of 2 times the square root of 64 times the square root of x to the fourth. Okay, what that leaves you is square root of -1 is going to be I. Square root of 2 can't touch, doesn't change because it's prime. Square root of 64 is 8. The square root of x to the fourth is x squared. So on the outside, we'll have 8I times x squared, square root of 2. And that's because we can't touch the square root of 2. All right, here we get some addition with complex numbers. We have 5 plus 7I minus a -3 plus 2I. Remember, when it comes to addition and subtraction, it's all about combining like terms. So if we have 5 plus 7I quantity minus -3 plus 2I. Okay, 5 minus a -3 gives you 8. 7 minus a positive 2I gives you 5I. Okay, 5 minus a -3 gives you 8 because you're really adding it. And then 7I minus 2I gives you 5I. All righty, here we got another one. We're going to solve it. Going to turn out to be having to simplify using I. So we have 7x squared plus 63, all set equal to 0. So first step, isolate the variable. We reverse PEMDAS, so we're going to minus 63 on both sides. That's going to give us 7x squared is equal to a -63 because those two cancel out. So we divide by 7 on both sides. We get that x squared is equal to a -9. Now we take the square root of both sides, which shows that x is equal to plus or minus 3i. Because 9 can be broken down. -9, square root of -9 can be broken down into the square root of -1 and the square root of 9. Square root of 9 is 3. Square root of -1 is I. So all that we are left with is x is equal to plus or minus 3i. And we have to put the plus or minus in because we used square root. It could be a positive, it could be a negative in that case. All right, last one, 5. Says, what are the values of x and y when 4 plus 2i minus x plus yi is equal to 2 plus 5i? So 4 plus 2i minus x plus yi is equal to 2 plus 5. So in this case, what we want to do is we want to take our real portions and set them equal to each other. So 4 minus x is equal to 2. Okay, so what value can we put in for x that would simplify this? Well, that would be x is equal to 2. Next one, 2i plus yi is equal to 5i. So 2 plus what value would give you 5? Y has to be equal to 3. Pretty simple. Or -3. Dang it, because it was a minus. Dang it, dang it, dang it. I'm better than that, but it's okay. So here's what we've done. We found the greatest common factors of sets of numbers. That was way back in August. when we were talking about factoring, this whole section is going to be about factoring. One of the beautiful things about factoring quadratic equations is it makes it a simple algebraic way that we can find the roots. So remember, the roots are the x-intercepts or the zeros. They're all equivalent terms. Okay, so we're trying to still find roots, but we're going to do it wholly algebraically today. So first thing is we're going to write quadratic equations in the standard form, and we're going to solve quadratic equations by factoring. Okay, standard form of a quadratic equation is ax squared plus bx plus c is equal to 0. Okay, the factored form. Okay, when you're talking about factored form, we're given equations that are listed like ax squared plus bx plus c. And those are going to be equal to 0. That's the standard form. The factored form is broken down into two binomials, which would be like a plus b, a minus b. So we're taking it from this form, putting it into this form. In other words, we are reversing FOIL. Okay, FOIL, we're given in this form, and we put it into that form by multiplication. The factor, we're reversing FOIL. Okay, and the FOIL method, your other vocabulary term. It's taking the first terms, multiplying by each other, the outside terms, the inside terms, and the last terms, and multiplying them all together. Okay, and there's a nice diagram of how FOIL works right here. So it says to multiply two binomials, find the sum of products of the first terms, the outer terms, the inner terms, and the last terms. More or less, you're repeating the distributive property twice. You're taking this first x and you're going to multiply it against both of those two terms. You take this 6 and multiply it against both of those two terms. Okay, so first, outside, inside, last. Okay, pretty simple stuff. We've done it before. We actually just did it when we were talking about multiplying complex numbers. So FOIL should be strictly review for you guys. All right, first one. So we'll write a quadratic equation in standard form with 1/2 and -5 at its roots. Okay, so more or less what they're giving us is we have the two x-intercepts. So at the point where y is equal to 0, the x values of this equation are equal to 1/2, and x is also equal to a -5. Okay, to get these into their binomial terms, what we want to do is we want to make it set so that is equal to 0. Okay, the first one, x is equal to a -5, is pretty simple. We add 5 on both sides. We have x plus 5 is equal to 0. Okay, this would be our first binomial term. Okay, this one is a little bit tougher. Okay, anytime that you have a fraction, just understand that you have multiplication involved. So the first step in getting it set equal to 0 is to multiply by 2 on both sides. That gives us 2x is equal to 1. Okay, and then we minus 1 on both sides. So 2x minus 1 is equal to 0, and that's our second binomial term. At this point, we have our factored form. 2x minus 1, x plus 5. Okay, to put it into the standard form, which they want, we have to carry out FOIL. So 2x times x gives you 2x squared. 2x times a positive 5 gives you plus 10x. -1 times x is a -1x. -1 times 5 is -5. Okay, after you do all of the multiplication, you can simplify like terms, your 10x and your -x. So that gives you 2x squared plus 9x minus 5. Okay, and those that set equal to 0 is our quadratic equation set in standard form. Okay, so you can see actually this process, what I just did, it's kind of the whole flip of the goal of this section. So we're given the roots at the very beginning because x was equal to 1/2 and x was equal to a -5. And then we get them set equal to 0. That gave us our binomial, which we're able to multiply. Going forward, we're going to be given this, and we're trying to get it to this. Okay, but it's nice to be able to go back and forth. Okay, so this problem, we were given the roots. They asked us to write the equation. So the first step, set them equal to x. Second step is to get them set equal to 0. Okay. Once we have that, now we can multiply. Using FOIL, you can see we get 2x squared minus x plus 10x minus 5. And then we simplify common terms or like terms. So this negative x and this plus 10x, they combine to be 9x. You can't combine 2x squared with that x because the x squared is a different term than x. And we have no other constant to combine. So our final answer would be 2x squared plus 9x minus 5. Okay. What allows this to happen is what's known as the zero product property. You all know, and you learned in elementary school, that anything multiplied by 0 is 0. The zero product property takes that to the next level. It says for any real numbers, a and b, if a and b is equal to 0, then either a must be 0 or b must be 0 or both must be 0. That's the only way you can have two terms multiply to each other and equal 0. There are no other ways that can happen. Okay, because anytime you're multiplying anything by 0, it turns out to be 0. Okay, the zero product property is what allows us to take these binomials and set them equal to 0 and solve and find our roots. That's because the binomials are the factored form of our standard equation, our standard quadratic equation. Give you a second to write that down while I take a drink. All right, it seems like multiple people are having a problem with the Zoom session today. Okay, first type of factoring that you're going to cover, it's called factoring out the GCF. Okay, the greatest common factor. Okay, the greatest common factors between both of these terms. What that means is we're going to factor out, inclusive of variables, what is encompassed in both of these two terms. So we have 9y squared plus 3y. And since they're set equal to 0, we'll be able to find the roots of this parabola. Because if we were to plug this into a graphing calculator or into Desmos, we would get parabola, right? So solving, we have 9y squared, and that's plus 3y. Is that equal to 0? So I'm thinking to myself, what number can be multiplied into 3 and 9? Okay, well, that's an easy one. 3. Right? Is the variable represented in both? And we have y here and we have y squared. So y is represented in both terms. So I can take out a y as well. 9y squared divided by 3y is going to give me 3y. 9 divided by 3 is 3. Y squared divided by y is y. Okay, 3y divided by 3y is equal to 1. And they're set equal to 0. At this point is where the zero product property kicks in. These two multiplied by each other have to, one of them must be 0 or both of them must be 0. So we set them equal to 0 and solve. So 3y set equal to 0. We divide by 3 on both sides. We get that y is equal to 0. Okay, 3y plus 1 set equal to 0. And then we solve for the variable. We minus 1 on both sides. We have 3y is equal to a negative 1. Divide by 3 on both sides. And we get y is equal to a negative 1/3. Okay, what this means is that these are the roots of our quadratic equation. Okay, anytime that we factor a variable outside as a greatest common factor, that means we cross at the origin, okay, at 0, 0. Anytime it's set up like this, you know you're going to have a fraction. Okay, and just to emphasize the point, I'll actually plug it in decimals, that way you can see it. That page over there. So I'm not going to be able to use y squared, but 9x squared plus 3x. We graph it, check our zeros. There's negative 1/3, 0.333, and 0, 0. Those are our two roots. Okay, you can see it a little easier if I expand it, but you can see by factoring that and setting it equal to 0 and then solving, oh, you didn't see it. Dang it. Here's the first one. Here's the second one. This 0, 0 corresponds to the 3y outside of my factored form. This negative 0.333 repeating is the decimal version of 1/3. And you can see at this point, what I've done is I've broken them apart. I've set them equal to 0. And whatever I solve for when I get x or solve to get my variable, those turn out to be the roots of my equation. So factor out the greatest common factor of 3y. That's because 3y can be multiplied into both of these terms. So once we do that, we're left with 3y plus 1 times the quantity of 3y. We set it equal to 0 and solve. So y is equal to 0 here. And then y is equal to a negative 1/3. And like I said, those answers correspond to the x-intercepts of our quadratic. And anytime you have a case like this with a variable factored out, okay, and it has to be a variable factored out, it's not just the greatest common factor of the coefficients, that means that you cross at the origin. All right, so here we have another one. We have 5a squared minus 20a. Let's set equal to 0, and we're solving for the variable a. So we're finding its roots. A squared minus 20a set equal to 0. Okay, first step. Once again, I want to think of a term that can multiply into both of these terms, okay, inclusive of coefficient and variable if possible. understand that if this 20 didn't have an A, I wouldn't be able to factor out A. Okay, I can only factor out the greatest common factor if it's representative in both terms. Okay, since A is part of both of them, I know that an A is coming to the outside. Another number that can multiply into 5 and 20. Okay, thinking of that, well, that would be 5, right? So I know I'm going to factor out 5A. So 5A squared divided by 5A gives me A. And then a minus 20A divided by A gives me negative 4. Those are set equal to 0. 5A set equal to 0 and solve for A. Divide by 5 on both sides. Gives you that A is equal to 0. Crosses at the origin. Happen every time we have a variable factored out in the greatest common factor. And A minus 4 set equal to 0. Solve for A by adding 4 on both sides. Gives you that A is equal to 4 and 0. So on our graph, these are our x-intercepts. We're going to have one at the origin. We're going to have one at the x value of 4 on the xy coordinate plane. Okay, those are the solutions to our quadratic equation. So factor out the greatest common factor of 5A. Left with 5A and A minus 4. Set them equal to 0. A is equal to 0 once we solve. A minus 4 set equal to 0. A is equal to 4 once we solve. So our solution is 0 and 4. All right. With factoring, there are certain things that come up. Okay, there are 4 different possibilities. They're called perfect squares or perfect square trinomials. Okay, each of them are titled something different. First is we have the difference of squares. Okay, and what that's representative of is we're going to end up in a scenario where it's A squared minus B squared. Okay, and A and B are just representative. They're just, an example of this would be like x squared minus 81. They're both perfect squares, right? This factored form for the difference of squares will always be A plus B, A minus B. Okay, the difference of squares. Okay, so in this case, A squared is x squared, B squared is 81. The square root of 81 is 9. That's what allows it to be a perfect square. So the factored form of x squared minus 81 is x plus 9 and x minus 9. Okay, the luxury of this is you can always check yourself. It's nice to know them off the top of your head, but you can always check and run FOIL to get back to it. X times x is x squared. X times a negative 9 is negative 9x. 9 times a positive x plus 9x. 9 times a negative 9 is negative 81. Once we combine like terms, these two will cancel out. The negative 9x plus 9x, those come out to 0. And we're back to where we started as x squared minus 81. Okay, that's known as the difference of squares. Okay, the next one is the sum of squares. Okay, instead of having a subtraction sign in the middle, we have an addition sign. So the sum of squares states that a squared plus b squared, okay, is what's given to you. The factored form is going to turn into a plus bi times a minus bi. Okay, and that's because once you solve this, we'd be left with imaginary number. So for example, I could do x squared plus 25. Right? And they're saying solve it, solve it. Okay, well, it's set equal to 0. Set equal to 0, so I isolate my variable by subtracting 25 on both sides. That gives me x squared is equal to a negative 25. Then we take the square root like we did last week, and we're left with x is equal to plus or minus 5i. Right? So the factored form of this is x plus 5i and x minus 5i. Okay, that's the sum of squares. Those ones will never touch the x-axis. Okay, because if you're looking at it just as the base equation x squared plus 25, one, we have a positive a value, so our parabola is opening up, and we have a constant of 25, so our parabola starts at 25. 0, 25 is the vertex, and then it opens up above the x-axis. It'll never touch it. So that's why we have imaginary roots. All right. Last two work the exact same way. Okay. And they're known as your perfect square trinomials. Okay, these ones are a little bit harder to identify, but their format is a squared plus 2ab plus b squared. Okay, is your first one. Okay, and what that factors down into is a plus b, a plus b. Okay, an example of this would be, we'll say x squared plus, have this one be 9. That would be 6x. Just like that. If we wanted to factor this, because I know it's a perfect square trinomial, that breaks down into x plus 3, x plus 3. And to check myself, always run it through FOIL. X squared, x times x gives you x squared. X times a positive 3 is plus 3x. 3 times a positive x is plus 3x. 3 times 3 plus 9. Terrible 9. Combine your like terms, we're back to where we started. Just like that. Okay, your second of the perfect square trinomials. I'll write it just beneath it. The format really doesn't change that much, but it is a squared minus 2ab plus b squared. Okay, so an example of one of these would be x squared minus 12x plus 36. Okay, this factored form is x minus 6, x minus 6. The general form, because I forgot to write it, would be a minus b times a minus b. Okay, if you check it with FOIL, x times x is x squared. X times negative 6 is negative 6x. Negative 6 times x is negative 6x. Negative 6 times negative 6 is a positive 36. Combine your like terms, you're left with x squared minus 12x plus 36. Give you a second to write that stuff down. But the beautiful thing is the perfect square trinomials, you're not going to have to remember those off the top of your head. because I'm going to show you a method that works regardless if you have a perfect square. Okay, it's that box method of factoring that we went over in August. All right, so our first one says solve each equation. And you can see this fits our perfect square trinomials. Okay, it'll fit that bottom one. Off the top of my head, I know that this answer is x minus 3, x minus 3. That's just because I'm familiar with them. I have a lot of practice with them, right? But the way we can factor this without knowing that it's a perfect square trinomial is to use the box method. So x squared minus 6x plus 9. And we draw a box. Okay, first, a couple requirements that you need on your quadratic to allow the box method to work. The first one is you cannot have a negative a value. If you have a negative a value, you have to factor it out. Okay, as the greatest common factor of -1. So as long as our a value is positive or our leading term is positive, the box works just fine. Okay, so we're good there. Greatest common factors all factored out. We're awesome. So first step, we take this quadratic term and we put it in the upper left side. So that's x squared. Take our term for c and we put it in the bottom right. Okay, now we multiply these two together. 9 times x squared gives you 9x squared. Okay, and now I want to think of two terms when multiplied together will equal a positive 9x squared. That'll add up to equal a negative 6x. Okay, we'll think. 3 times 3 is 9. 3 plus 3 is 6. So those ones will work, except for they have to be negatives. So I have negative 3x and negative 3x. I put those into my remaining squares. Okay, I put them in. Now, going row and row, I factor out the greatest common factor. So the greatest common factor between x squared and a negative 3x is x. Greatest common factor between the negative 3x and 9 is negative 3. Okay, now columns. Do the same thing. Factor out the greatest common factor of each column. X squared and the negative 3x gives me x. Negative 3x and 9 gives me negative 3. So my two binomials are x minus 3, x minus 3. And I can always check myself by foiling. X times x gives me x squared. X times a negative 3 is negative 3x. Negative 3 times x is negative 3x. Negative 3 times 3 is a positive 9. Combine my like terms to get to x squared minus 6x plus 9. Okay, and I'm back to where I started. So I've checked to make sure that my binomials are correct. Now I have to use that zero product property. Set each of these equal to 0 and solve for x. We add 3 on both sides. Gives us that x is equal to 3. Okay, in other words, this would fall into a situation where the parabola has one solution, meaning that it's opening upwards and the vertex is on the x-axis, so the lowest point. And the vertex x value is going to be 3. The book just wants you to run with the perfect square trinomial. So x minus 3 squared, square root of that, x minus 3, solve for x, x is equal to 3. Okay, but like I said, the box method, it'll work if you have a perfect square trinomial. It'll work if you have a value that's not a perfect square. All right, on this one, y squared is equal to 36. Okay, this one is going to turn into the difference of squares. Okay, but first I have to get it into the standard form. Okay, y squared. I mean, I could solve this and take the square root and get plus or minus 6 as the value for y, but what fun would that be? We got to show how to factor it. But in order to factor it, we got to get it into standard form. I got to move the 36 from one side to the other. So I'm given y squared is equal to 36. I subtract 36 on both sides to get y squared minus 36 is equal to 0. This fits the difference of squares. Y squared is a perfect square. Negative 36 is a perfect square. So that's a squared minus b squared. As a factored version, breaks down into a plus b, a minus b. Okay, so in this case, since y squared is a perfect square of y, 36, the square root of 36 is 6. I know that my factored form is y plus 6, y minus 6. If I set those both equal to 0, because of the zero product property, and solve for y, I'm going to end up with y is equal to a negative 6 and y is equal to 6. Oh, helps if I put them on the right side. Could you use the box method on this one? Yes, you could. It's just a little redundant. You'd be looking for two terms that multiply to equal a negative 36 that add up to be 0. So that would be plus 6 and minus 6. So, and then you could carry out the box method that way. It's just the perfect squares is really the difference of squares is probably the one that you need to know off the top of your head the most, because it's the simplest and easiest one to remember. And it just makes you more efficient. So there's our difference of squares. Now we solve for y. And we get our solution set of negative 6 and positive 6. All right, let's get to a tough one. All right, here we go. Factoring trinomials. This one you can see it's not a perfect square. Okay, it's not a perfect square trinomial. This one will be a little different, but the box method solves it pretty easily. So we have x squared minus 2x minus 15 set equal to 0. First thing I want to check, I want to make sure that I have a positive a value. Okay, I have a positive a value. I am good there. Now I can proceed to my box. In the upper left-hand corner, I put my first term. The lower right-hand corner, I put my second term inclusive of sign. So since it's a negative 15, that's where they stay. Then I multiply these two together to get a negative 15x squared. So now I'm thinking of two terms that multiply to equal a negative 15x squared that add up to equal a negative 2. Okay, sign's important. So two terms I think of are negative 5x and positive 3x. Negative 5 times negative 5x times a positive 3x gives me negative 15x squared. Negative 5x plus 3x does give me negative 2x. So then I can fill those in, inclusive of sign. So if it's positive, I want to put positive. If it's negative, I want to put negative. Then working rows first, I factor out the greatest common factor. Between x squared and negative 5x, that is x. Okay, between the greatest common factor between 3x and negative 15 is a positive 3. Okay, between x squared and 3x, greatest common factor is x. Between a negative 5x and a negative 15, that gives me negative 5. Okay, those are my two binomials. So x minus 5, set them equal to 0, and x plus 3, set them equal to 0, and then we solve for x. So on this side, we add 5 to both sides to show that x is equal to 5. This one, we subtract 3 from both sides to show that x is equal to a -3. And those are the x-intercepts or the roots or the zeros of our function. All right, let's see how the book walks you through it. So factor the equation. So what the book tells you is that we want to find two terms that multiply to equal our term for C, or constant, that add up to equal our term for B, or our linear term, right here in the middle. Okay, so x plus 3, x minus 5. -5 times 3 is a -15. -5 plus 3 is a -2. So we're good there. You can also, at this point, check yourself for FOIL. Oh, that's something I forgot. One of the reasons why I like the box method, sorry to backtrack a little bit, is because it has built-in checks. Okay, the way the built-in checks work is if I were to match these where they match, they better be able to multiply to equal. X times x is x squared. -5 times x is -5x. -5 times 3 is -15. X times 3 is 3x. Okay, that's a built-in check with the box method, so we don't have to factor all these things, run it through FOIL and say, oh no, my answer doesn't work. Okay, it has a built-in check right there. It's a little bit nicer, a little bit more process-driven way to solve these equations. So back to the book, we set it equal to 0 when we solve. So x is equal to a -3. Then x is going to be equal to 5. All right, here's a really tough one. Trying to solve each equation, it's 5x squared plus 34x plus 24. Oh boy. Good thing is the box method doesn't even blink. It's the same process. 5x squared plus 34x plus 24. Set equal to 0. Okay, first thing I want to look for is, do I have a positive A term? So is my leading term positive? The answer to that is yes. So I can proceed to my box. If I put 5x squared in the upper left, put positive 24 in the lower right, and then I multiply those. 5 times 24 is 120. So that answer is 120x squared. Okay, here's where it gets tricky, because I need to find two terms that multiply to be a positive 120 that add up to be a positive 34. Okay, and for lack of a better way to do this, it's a lot of guess and check, to be honest. So what we could do is we can actually list out factors. The factors of 120. Okay, so the first one is 1 times 120. Okay, not even close to what we got to add to. It'll add up to 121 or 119. 2 and 60, add up to 62 or 58. That doesn't work. 3 and 40. Okay, that doesn't work either, because it'll add up to 37 or 43. But I'm getting closer. 4 and 30. Multiply to be a 120, will add up to be 34. Those are the ones I want to use. So I take 30x and I take 4x. And I fill out my box. Okay. Now, the process just stays the same. Factor out the greatest common factor of each row and column. Greatest common factor between 5x squared and 30x is 5x. And we'll multiply to be both of them. Greatest common factor between 4x and 24 is 4. Okay. Greatest common factor between 5x squared and 4x is just x. Greatest common factor between 30x and 24 is 6. Okay, now I can check myself. 6 times 4 is 24. X times 4 is 4x. 6 times 5x is 30x. X times 5x gives me 5x squared. So these binomials are good. Take them, set them equal to 0, and solve for x. One of them is real nice and easy. X plus 6 set equal to 0. Minus 6 on both sides to show that x is equal to a negative 6. Okay, 5x plus 4 set equal to 0. Minus 4 on both sides to give me 5x is equal to a negative 4. Divide by 5 on both sides gives me that x is equal to a negative 4/5. Okay, those are the roots of my equation. Okay, that's where my graph crosses the x-axis. You can see as long as you stick to the process, the box will handle any type of problem that's thrown at you. Okay, the one thing that it doesn't do well is the difference of squares, because it's just more work than it's really worth. So there's our factors. We set them equal to 0. We solve. Set it equal to 0 and solve. And we get negative 6, negative 4/5. Nick, you're not on your phone, are you? Why? You should be paying attention. You only have notes out, man. Did you write that one down? Do you know how to do it? That's why, that's the look on your face right now is the exact reason why you should pay attention. Right? You're playing on your phone.
No, just now.
Yeah, you were playing on your phone when I went over. That's just one of those things. All right, last one. Says the entrance to an office building is an arch in shape of a parabola whose vertex is the height of the arch. The height of the arch is given by h is equal to 9 minus x squared, where x is the horizontal distance from the center of the arch. Both h and x are measured in feet. How wide is the arch at the ground? So this one's a little bit tricky. Okay, they give us a parabola. Okay, and what we're going to end up doing is we're going to end up factoring it and setting it equal to 0. Okay, the key thing is it says it's at ground level. So what we can do is we know that 0 for h plugged in, because it's at ground level, is equal to 9 minus x squared. Okay, if you wanted to rework that to get them to a more standard form, it would be x squared minus 9 is equal to 0. Okay, because you add x squared and then you subtract 9. That's the way you get it. This falls into the difference of squares. X squared is a perfect square. 9 is a perfect square. So it would be x plus 3, x minus 3 as our factored form. Because we'd be looking for two numbers that multiply to equal a negative 9 that add up to be 0. So 3 and negative 3 work there. Okay, here we're talking about distance. So we want to find where these would actually touch from the center. So x plus 3 is going to be kind of our x-axis. So we're still trying to find the roots, x minus 3. Set them equal to 0. This side we get x is equal to negative 3. This side we get x is equal to a positive 3. The distance between these two is 6 feet from a 3 and negative 3. Okay, it's just factoring it again. That falls into a difference of squares. So factor the equation to find the roots. 3 plus x, 3 minus x. So x is equal to 3. X is equal to a negative 3. The horizontal distance from the center of the arch is half the distance is 3. Oh, it said from the center? It's talking the whole thing. X is the horizontal distance from the center. So the total arch is 6 feet. From the center to one side would be 3 feet. Huh. No, I was right. The jerks, I was right. Right there. But you can see it's the same exact type of thing. We solve it, and then we just have to put it into terms that they are used to. So